Programmable read-only memory. We shall see in this session about combinational programmable logic devices and programmable read-only memory in particular. A combinational PLD is an integrated circuit with programmable gates divided into an AND array and an OR array to provide an AND or sum of product SOP implementation. PROM, programmable read-only memory. It can be constructed using fixed AND array and programmable OR array. Fixed AND array is nothing but our decoder. So the inputs are given to the decoder and the outputs are taken from the programmable OR array to construct a PROM. Array logic. A typical programmable logic device may have hundreds to millions of gates interconnected through hundreds to thousands of internal paths. So for this, we are going to see how to construct a gate. Now here, we can consider OR gate. The conventional symbol of an OR gate we can see here. So here we have got 1, 2, 3, 4. 4 inputs are there to the OR gate and we have got 1 output. So this is how we represent the inputs to a conventional OR gate. When we come to represent an array logic symbol, we need to represent it like this. So this is an OR gate where we have 1, 2, 3, 4 inputs as vertical lines and we'll have 1 output as usual. So now if I put a cross mark over 1 at this position, it represents I have connected 1, the variable 1 to the input of OR gate. If I put a cross mark over 4 at this position, it represents I have connected the 4th variable as an input to this OR gate. So for this particular OR gate, 1 and 4 are the inputs. 2 and 3 I have not put a cross mark, which means 2 and 3 are not the inputs for this particular OR gate. This is how we represent an array logic or array logic. Read-only memory. So this is a block diagram to represent read-only memory. We can see 2 power k into n. So this k represents the address lines, number of address lines. So k inputs are there, so 2k address lines are there. And we have n outputs, which are the data. So the number of words in the ROM is determined from the fact that k address input lines are needed to specify 2 power k words. This is the construction of ROM. Let us see how to construct a 32 cross 8 ROM. 32, which means 2 to the power 5 is 32. So I can have 5 combinations I0, I1, I2, I3, I4, which can generate 32 locations. So this are called to be 32 address lines. So from 0 to 31, I've got 32 address lines, which means in each address I can store exclusive data. So each data will be distinct. I can store 32 distinct data using this. So to obtain this 32 address line, I am using a 5 cross 32 decoder. Now the outputs have to be obtained. That is 8 outputs. So A0 to A7. These are the 8 outputs of your ROM. So 32 inputs, 32 address lines and 8 data lines. So A0 to A7 OR gates will give us the outputs. Now we can see each output of the decoder represents a memory address. As just now I mentioned, there are 32 distinct address locations and each OR gate will have 32 inputs. So from 0 to 31, from 0 to 31, each one is going to be an input for each OR gate. So again from 0 to 31, I'll have input to this second OR gate. From 0 to 31, I'll have 32 inputs for this particular OR gate. So each OR gate will have distinct 32 inputs. Now a 2 power k n ROM will have an internal k power 2k decoder and an n OR gate. Let us see the truth table of read-only memory. Here we can see the inputs. The inputs are I0, I1, I2, I3 and I4 and outputs are represented from the OR gates. It is A0 to A7. So in this particular, let us consider the location 00001. So in this address location, the data that is stored will be 0001101. So this is the data that is stored in the address location 00001. Similarly, if I consider 11111. This address location, the data that is stored in this location will be 00110011. Now, how to program this? We have got a 5x32 decoder. Just now we saw this, and we have got the 8 OR gate. So this is going to be your 32x8 ROM. So now here we are going to represent the cross mark indicates inputs are given and the blank represents there are no inputs. So if I want to represent, say if I want to consider address location 3. So address location 3, certain data are stored. What is the data that is stored in address location 3? Since there is a cross mark, this is going to be your 1. There is no cross mark, so it has to be 0. Here I have a cross mark, so it has to be 1. This again 1. This is 0, 0, 1 and 0. So here this is going to be the content that is stored in the address location 3 is 10110010. So what is the output that we will get? We will also get the same output, which means only the address line 3 will be enabled. All the remaining 31 lines will be disabled. So I will directly get the output that is stored in the address location 3. So the output that I will be getting is 10110010. Fine. Okay. Now let's consider the address location 30. So let me delete this. So let's see what will I get. Let me use a different color. So if it is going to be address location 30, what will be the output here? So this is going to be 0, 1, 0, 0, 1, 0, 1, 0. So my output will be 0, 1, 0, 0, 1, 0, 1, 0. So this will be my output if I'm going to use address line 30. Now, for an example, let us consider to design a combinational circuit using a ROM. Here the circuit accepts a 3-bit number and generates an output binary number equal to the square of the input number. So let's write the truth table. The truth table should contain inputs and outputs. So inputs are, it's a 3-bit number. So the inputs are 3 inputs, so 3-bit. So we can have 8 combinations. Correspondingly, the output is going to be the square of the input number. So the square of the input number, let us consider the decimal equivalent for this. So 0, 1, 2, 3, 4, 5, 6 and 7. So the decimal equivalent will be 0, 1, 4, 9, 16, 25, 26 and 36 and 49. So this is the decimal equivalent. Now we need to write the output in terms of binary. So since we have up to 49, I should have 2 to the power 6. Only then I can have 64 combinations. So I am going to write the equivalent of decimal here. I can use the weighted code. So this will be 1, 8421. So this is 2. This is 4, this is 8. 8421, we all are familiar. So to increase the weighted code, so this position has to have the weightage of 16 and this position has to have the weightage of 32. So how do I represent? For example, let us consider 49. If it is 49, it has to be 32 plus 16 plus 1. This only will give you 49. So this way we can fill the table. So we have completed the truth table. After completing the truth table, we can see here B0 is going to be 0, 1, 0, 1, 0, 1, 0, 1. Same way your A0 is also going to be 0, 1, 0, 1, 0, 1, 0, 1. Which means I can write it as A0 is equal to B0. So one bit is directly obtained. Now when you consider the second bit B1, it is totally entire B1 is going to be equal to 0. So therefore I can omit this A0 is already equal to B0 and B1 is equal to 0. So the remaining B2, B3, B4, B5 alone, I am going to bring it into the next table. So I have the same A0, A1, A2 and B2, B3, B4, B5. So these are going to be my final outputs and these are my inputs. So this is our truth table. Now we have to represent this as a block diagram. So this is going to be your 8x4 ROM. How do we got this as 8? 2 power 3 is 8. So I'm going to have 3 combinations, A0, A1, A2. And we also know A0 is equal to B0 So therefore, directly we have got A naught equal to B naught, and we also know B1 equals 0. So therefore, this is B1 equal to 0. So the remaining alone will construct a circuit like this. So this is how we can implement a 8 cross 4 ROM to obtain the square of a given binary number. Thank you.